Welcome viewers. Today we are going to discuss Taylor series of complex variables. If we have a function f of a real variable x, then we know that this function can be expressed in power series of x under certain conditions. The condition is that function fx has derivatives of all orders, and we know that how to express cosine function, sine function and exponential functions in power series of x. Now, the question is, can we express these functions when they become function of complex variables in the form of a power series? So, that is what we are going to discuss today. But before we actually discuss Taylor series in complex variables, I will first introduce some basic concepts related to series. So, to start with, let us say Z1, Z2, Zn forms an infinite sequence of complex numbers. Then this sequence converges to a limit c if for each epsilon positive there exists n such that magnitude of Zn minus c or modulus of Zn minus c is less than epsilon for each n greater than n. This can be explained graphically, like on the z plane we have numbers z1, z2, z3, zn, zn plus 1 and so on. Let us say this is the number c, then can we draw a circle at c with radius epsilon in such a way that all the points after some n, they all lie in this circle. So, if we can, for given epsilon we can find sufficiently large n, so that after some n all the points will lie in this circle. If this is possible, then we say c is the limit of the sequence z1, z2, zn. Which is not convergent is said to be a divergent sequence. Now, we state a theorem. According to this, a sequence z1, z2, zn, which is in which the zn can be expressed as xn plus iyn, this sequence converges to a limit c is equal to a plus ib if and only if the sequences of real parts x1, x2, xn and sequence of imaginary parts y1, y2, yn converges to their respective parts a and b, then we say this sequence is convergent and it converges to c is equal to a plus ib. The idea is that if we have a complex sequence, then it can be equivalent to two sequences x1, x2, xn of real parts and y1, y2, yn of imaginary parts, and if these two sequences converge to a plus ib, a and b respectively, then the sequence of complex numbers will converge to c is equal to a plus ib. Now, I am not proving this result. Further, we define series. So, let W1, W2, Wn be a sequence of complex numbers, then an infinite series is defined as summation I is equal to 1 to infinity Wi is equal to W1 plus W2 plus Wn and so on. So, this is a series. So, let Sn defines the partial sum of first n terms of the series. That means, we have Sn is equal to W1 plus W2 plus Wn, then Rn is sum of remaining terms starting from Wn plus 1 plus Wn plus 2 and so on. Then Rn is called the remainder of the series, and if the sequence of partial sums S1, S2, Sn converges to S, then the series 1 is said to converge. So, this S is equal to Sn plus Rn. Power series is defined as a series in powers of z minus a. It is an infinite series of the form summation n is equal to 0 to infinity C m z minus a raised to power m and in expanded form we write this series as C naught plus C1 z minus a plus C2 z minus a square plus and so on. We call it a power series because here each term is power of some power of z minus a. In this case z is a complex number, C naught, C1 etc. these are constants called coefficients of the power series, and a is called the center of the series. This a is called center of the series. When a is equal to 0, then this series will be a power series in powers of z only. Now, in this example, I will check the convergence of the series 1 plus z square and so on. One can notice that it is geometric series. So, if I consider the first n terms of this geometric progression, then Sn is equal to 1 minus z raised to power n plus 1 over 1 minus z. This is the well known formula for sum of n terms of the geometric series. Then this can be written as 1 upon 1 minus z minus z n plus 1 over 1 minus z. I write this as S and this as Sn. Now, when z is less than 1, then this term will tend to 0 as n tends to infinity, because as we increase powers this term will become smaller and smaller. So, this will tend to 0, and that simply means that Sn converges to 1 upon 1 over 1 minus z. So, we can say that this geometric progression will converge to 1 over 1 minus z provided mod z is less than 1. In this case, radius of convergence is 1, and this series is divergent for mod z greater than equal to 1, as z raised to power n will become larger and larger as n increases. So, this series is divergent for mod z greater than equal to 1. In another example, if we consider the exponential series, which is z raised to power m divided by factorial m, is an infinite series, or this is equal to 1 plus z square by factorial 2 plus z cube of factorial 3 plus and so on, then this exponential series is convergent for all z, and this can be proved by the ratio test. So, we have seen that the power series may converge for all z. The other possibility may be that given power series may converge for some values of z is equal to a, and in the third case power series may converge for some values of z, but for others it may not converge. Like we can say that power series is convergent in the region when z minus a is less than r, but for others it may not converge. So, these are different possibilities. So, this theorem says that if we have a power series centered at a with radius of convergence r, and the series is given as, the series is such that limit as m tending to infinity of Cm over Cm plus 1 is equal to lambda, then radius of convergence of the series is lambda. Also, if Cm raised to power minus 1 by m, the limit m tending to infinity is lambda, then again the radius of convergence is lambda. I am not giving the proof of these results. Next, let the series with non-zero radius of convergence r, let us say it is represented as this, then the sum of the series is a function of z. So, this series converges and this will be a function of z. So, we say the sum of the series is a function of z. Now, we say f z is represented by power series. So, if we can write f z this way, then we say that f z is represented by a power series, or f z is developed in powers of z, such type of representation is unique, and uniqueness of power series is established in the form of the theorem. It suggests that summation a n z n plus summation b n z n, let us say we have two different series. These are power series which are convergent for this region mod z less than r being positive. Then they have same sum, let us say this also represent f z and this also represent f z, then a n and b n will be equal. So, if there are two power series representing the same function, then that series has to be unique. There is one more result, again we are not giving the proof of the theorem, and according to this, if we have a power series C naught plus C 1 z plus C 2 z square, then the derived series which is obtained by term differentiation of the given series as this, if we differentiate this term by term, then it is C 1 plus twice C 2 z plus thrice C 3 z square and so on, or we can write in the compressed form as this, then this is a power series for the function f dash z. So, if we write it in the form of theorem, then summation C n z minus a raised to power n and summation n c n z minus a raised to power n minus 1, n varies from 1 to infinity in this case and 0 to infinity in this case, then they have the same radius of convergence and they converge to, if this converge to f z, then this will converge to f dash z. Next, if we have a power series with radius of convergence positive r not equal to 0 and let f z is represented as this whenever mod z is less than r, or the radius of convergence of this series is r, then f z is analytic within the open disk center at a radius a, center at a and of radius r, and f dash z is equal to summation n is equal to 1 to infinity n c n z minus a raised to power n minus 1. This means that if this power series is represented as f z and f z is analytic, then its derivative will also be represented as a power series and it is analytic. Not only this, but if you differentiate this series term by term, then this will represent the function f dash z. So far we have discussed some concepts related to sequence, series, power series and convergence. I have described these concepts and given you some results in the form of theorems, but I have not proved those theorems. And now we are in a position to discuss Taylor series. To develop Taylor series, let us consider an analytic function f z. By this I mean to say that f z is analytic in the neighborhood of a point z is equal to a. Let us say C be a circle lying in this neighborhood having center at a. According to Cauchy's integral theorem, analytic function f z can be represented as f of z is equal to 1 upon 2 pi I integral over the closed curve C of f z star divided by z star minus z into d z star. That means, we are integrating this integrand over the curve C. Let me explain this. I have in the z plane the function f z which is analytic in a domain, and in this domain I have a point A, and at A I draw a circle. I call that circle is C1 and Z is a point inside this circle and Z star is a point inside, Z star is a point on the circle C1. Then 1 upon Z star minus Z is equal to 1 upon Z star minus A minus z minus a. So, I have added and subtracted a here, and by this, from this I can write 1 upon z star minus a into 1 minus z minus a divided by z star minus a. So, what I am doing is I am taking z star minus a outside this parenthesis. Now, here this is the point z inside the circle and z star is on the boundary. That means, this distance z minus a is less than the distance z star minus a. So, if I denote q as z minus a divided by z star minus a, then I know that modulus of q is less than 1, and if it is less than 1, then this is a geometric series, and in fact these are the first n terms of geometric series 1 plus q square plus q n, and we know that this sum is equal to 1 minus q raised to power n plus 1 over 1 minus q, q being z minus a divided by z star minus a. So, if I take this term on this side, then it is 1 plus q square plus q n plus this term I am taking on the other side. So, this is equal to 1 over 1 minus q. Now, with this simplification, we come back to the integral 1 upon 2 pi I integral f z star over z star minus z d z star representing f of z, and we write it as 1 upon 2 pi I f z star minus z into z star minus a dz star. This term corresponds to this 1 plus z minus a into 2 pi I integrals f z star minus a whole square dz star. This will correspond to the second term, and the last term will be this. So, we have f z represented as this. Here r n z is equal to z minus a raised to power n plus 1 upon 2 pi I integral f z star minus a raised to power n plus 1 into z star minus a dz star. And we know from our formulae for derivatives, f n z naught is equal to factorial n over 2 pi I integral f z over z minus z naught raised to power n plus 1 dz. Now, this is a known formula for n is equal to 1 to n. So, nth derivative will be given by this integral over the closed curve C. Using this, one can write our expression as f of z is equal to f of a plus z minus a over factorial 1 f dash a plus z minus a square by factorial 2 as multiplied by f double dash a and so on, and the last term is z minus a raised to power n divided by factorial n f n a plus the remainder term r n z. Now, the remainder term r n z, which is z minus a raised to power n plus 1 over 2 pi I f z star divided by z star minus a n plus 1 into z star minus a dz star is integrated over the closed curve C. This can be simplified and may be shown that this tends to 0 as n tends to infinity, and with this the analytic function f z is represented as summation f m z over factorial m into z minus a raised to power m. At a is equal to 0, this series is called Maclaurin series of f z. The series converges if and only if limit r n z tends to 0 as n tends to infinity. So, this is yet to be proved, and we can notice that z minus z star modulus is positive and f z is analytic. That means, f z star over z minus z star is less than M for all z star in C, and third is that integral f z dz is always less than equal to m times L, where f modulus of f z is less than m and L is the length of this closed curve C, C being a circle. So, L is equal to 2 pi. If it is a unit circle, then L is equal to 2 pi. Using these facts, we simplify the expression for R and Z, which is given as this. So, let us consider the modulus of R and Z, and this is modulus of this value divided by modulus of 2 pi I, which is 2 pi, and modulus of this integral, and this is written as m times 1 upon R n plus 1 into 2 pi, and this simplifies to modulus R n is less than m times z minus a divided by R raised to power n plus 1, and this tends to 0 as n tends to infinity, because z minus a divided by R is less than 1, and as n increases, this power increases, and this is less than 1. So, this will tend to 0 as n tends to infinity. So, this proves that R n tends to 0 as n tends to infinity, and that is why we have the Taylor series representation. Now, we will have formally state the Taylor's theorem. According to this, let f z be analytic in domain D, let z is equal to a be any point in D, then there exists a unique power series with center at A, which represents f z. So, f z is represented as n is equal to 0 to infinity b n z minus a raised to power n, where the coefficients b n are given by 1 upon factorial n multiplied by f n a, the nth derivative of f z evaluated at center z is equal to a, and this is true for all values of n 0, 1, 2 and so on. So, this is the Taylor's series, and the representation is valid in the largest open disk with center A that is contained in the domain D. By this I mean to say that analytic functions have derivatives of all orders. That is why we can represent it as a Taylor series, because we have to calculate different b n's, and b n's they are evaluated in terms of derivatives. Analytic function can always be represented as power series, because they have derivatives of all orders, but this is not true for real functions. Real functions have derivatives of all orders, but cannot be represented by power series. So, that is the basic difference between function of a complex variable and function of a real variable. Next, if every power series with a non-zero radius of convergence is a Taylor series of some function represented by that power series. So, let us say we have a power series b n z minus a raised to power n, n is equal to 0 to infinity, and let us say it represents a function f z, then f z is the Taylor series for the, this is a Taylor series for the function f of z, and in this case f dash z is equal to b 1 plus twice b 2 z minus a plus and so on, implies that b 1 is equal to f dash a. So, if you differentiate this, we will get b 1 is equal to f dash a, and f n z is equal to the nth derivative of z is equal to factorial n over b n plus n plus 1 factorial b n plus 1 z minus a plus and so on. So, this is when we differentiate this series n times, and if you put z is equal to a, then all these terms will vanish and will have b n is equal to f n z over factorial n. And by this I mean to say that if we can express, if this series is equal to f z, then this is nothing but the Taylor series. So, it is a unique representation. So, this is what we have. So, given series is a Taylor series for the function f of z. So, let us illustrate with some examples. So, we have been given a function 1 over 1 minus z and we have to expand it in powers of z. So, we know that this function is analytic at z is equal to 0. If we have to express this in powers of z, then it should be analytic at z is equal to 0. So, it can be represented in Taylor series. At z is equal to 1, function is not analytic, it is not defined at z is equal to 1. So, there is no question of analyticity at z is equal to 1. Then if we write f z is equal to 1 over 1 minus z, then f dash z comes out to be minus 1 into minus 1 multiplied by 1 over 1 minus z square. So, we evaluate the derivative at z is equal to 0 and b 1 comes out to be 1. Similarly, for the second coefficient b 2, we have to evaluate the second derivative at z is equal to 0. So, evaluate the second derivative, it comes out to be minus 1 into minus 2 into 1 over 1 minus z cube, and this simplified to factorial 2 over 1 minus z cube evaluated at z is equal to 0. This gives me b 2 is equal to 1. Similarly, we can calculate f and z is equal to factorial n over 1 minus z raised to power n plus 1. This is the nth derivative, and evaluated at z is equal to 0, this gives me b n is equal to 1. So, if we write down the coefficients, values of these coefficients, then f z is equal to 1 plus z square plus z n and so on. So, this is the power series, or we call it a Taylor series of the function 1 over 1 minus z. This is a Taylor series. Further, we have seen that this series converges to 1 over 1 minus z, because this is geometric progression, geometric series. So, this converges to 1 over 1 minus z. So, this is a unique representation, it is 1 over 1 minus z and its power series is this. Its Taylor series is 1 plus z square plus z raised to power n and so on. So, this is a unique representation. This series which we expand in powers of z, that means the center is 0, this is called as Maclaurin expansion or Maclaurin series for the function f z is equal to 1 over 1 minus z. This circle of convergence is modulus z is equal to 1, because the maximum distance from the singular point of the function, singular point is the point where function is not analytic, and we have seen that this function is not analytic at z is equal to 1. It is analytic at z is equal to 0, but not analytic at z is equal to 1. So, the maximum distance is 1. So, circle of convergence is modulus z is equal to 1. So, series converges at all points inside this circle mod z is equal to 1. So, this we try to explain the concept of Taylor series for the known function. Now, we try to expand E z in Maclaurin series. So, we know that this function E z is analytic everywhere. So, we can try to represent this function as a Maclaurin series. For this, we need to calculate various derivatives. So, derivative of E z is E z, and in fact, the nth derivative of E z is also E z. So, this gives me that b n is equal to 1 upon factorial n, and this means E z is represented as summation n is equal to 0 to infinity 1 upon factorial n z raised to power n, or in expanded form it is 1 plus z square by factorial 2 and so on, plus z n over factorial n and so on. So, the Maclaurin series for the exponential function is given as this. Further, if this is Maclaurin series for the function e raised to power z, then what will be the Maclaurin series for the function e raised to power minus z? So, if we replace z by minus z here, then we will get the Maclaurin series for the function e raised to power minus z. So, doing this, proceeding this way, we will say that E minus Z is equal to minus 1 raised to power n factorial n divided by factorial n into Z raised to power n, and that gives me 1 minus Z plus Z square by factorial 2 plus minus 1 raised to power n Z raised to power n factorial n and so on. So, we have alternating positive and negative terms in this series. Now, since both the functions E z and E minus z are analytic, so both the series are convergent, and if we multiply them, then E z into E minus z is equal to summation n is equal to 0 to infinity 1 over factorial n Z raised to power n. This is the series for E raised to power z, and this is the series for E raised to power minus z. So, if we multiply them, then this is what we have, the series in expanded form for E z, this is the series expanded form for E minus z. If we multiply, then we collect various terms. So, we first multiply 1 by this plus z times this plus z square by factorial 2 times this and so on. So, this way we multiply the two series and let us then collect various terms. So, proceeding in this manner, this is the first term, then z is multiplied by the second series. So, we will have z minus z square plus z cube by factorial 2 and so on. Then z square by factorial 2 is multiplied by this series, this is the next term, then the next term and so on. So, now you can notice that if we combine these two terms, it is 0. Combining the powers of z square, this is z square by factorial 2, this is z square by factorial 2. So, they will be simply z square and this minus z square. So, they cancel out. Similarly, if you consider z cube by factorial, the next term z cube, then this and this term will cancel out and this term and next term here will cancel out. So, this way each and every term, each and every power will be 0, and what we have simply the first term 1. So, that proves the result that E z into E minus z is equal to 1. So, we can multiply infinite series term by term and result remains unaffected. So, this is the result. We already know that E z into E minus z is equal to 1, but by actually multiplying two power series, this also gives us 1. So, term by term multiplication of power series is possible. Now, in this example, we try to express log 1 plus z in powers of z. For this purpose, we consider f z is log of 1 plus z, differentiating and then writing z is equal to 0. This gives me b naught is equal to this. Simply writing z is equal to 0 here, it will give me b naught, and this is nothing but 0 because log of 1 is equal to 0. Then differentiating this, that is 1 over 1 plus z, and then writing z is equal to 0 gives me b 1 is equal to 1. Further, we compute the second derivative by differentiating f dash z, and this gives me minus 1 over 1 plus z square, and at z is equal to 0, this gives me f double dash z is equal to minus 1, giving me b 2 is equal to minus half. Next, we calculate the third derivative as 2 times 1 plus z cube, and evaluating this derivative at z is equal to 0 gives me b 3 as 1 by 3 and so on. We can calculate b n plus 1 z, we calculate b n plus 1 from the n plus 1 at derivative, and this comes out to be minus 1 raised to power n divided by n plus 1. Substituting these values, I will get ln of 1 plus z is z minus z square by factor z square by 2 plus z cube by 3 and minus 1 raised to power n z n plus 1 over n plus 1 and so on. So, that will be ln 1 plus z expansion. So, this is the Taylor series, and since the center is 0, we can call it as Maclaurin series. Similarly, from this we can derive Taylor series for the function ln of 1 minus z by replacing z by minus z in this series. So, we will have the series with all negative terms. So, if I subtract the two series, then it is ln of 1 plus z minus ln of 1 minus z is 2 times z plus z cube by 3 plus z 5 by 5 and so on. And this expression can also be written as ln of 1 plus z over 1 minus z is equal to 2 times z plus z cube by 3 plus z 5 by 5 plus and so on. So, in this case I have expressed ln 1 plus z over 1 minus z, this function as a power series in z. So, this is Maclaurin series for this function ln 1 plus z over 1 minus z. So, I am not calculating the power series of this function from the basic principle, but I am applying results for ln power series of ln 1 plus z and power series of ln 1 minus z, and I get this result. Now, in the next example, we find the first 3 terms of Maclaurin series for the function E z sin z. Now, in this case we have to expand this function about z is equal to 0. So, if you put z is equal to 0, then f of z will be 0, and that means b naught is equal to 0. We calculate various derivatives of this function, and for first derivative it is E z cos z plus sin z, that gives me b 1 is equal to 1. Differentiating this again give me the second derivative, and it is E z into cos z plus sin z minus E z times derivative of cos z plus sin z, that is minus sin z plus cos z, and putting z is equal to 0 gives me 2 into E z cos z, that implies that b 2 is 1. Then f triple prime z is computed as this by simply differentiating this, and that gives me b 3 is equal to 2 by factorial 3 minus 1 by 3, and simplifying we will get this Taylor series for the function f z is equal to E z sin z. So, this series has radius of convergence r is equal to infinity, because there is no singular point for this function. This function is analytic everywhere, because E z function is analytic everywhere, sin z function is analytic everywhere. So, the product will be analytic everywhere. So, radius of convergence will be infinity, or we call such a function as entire function. We have the number of functions so far. We have obtained their power series by applying the formulae, by calculating derivatives, but now we will develop some simpler methods for obtaining power series. We do not have to always find the derivatives and then express it in a power series, because there is a uniqueness of power series. So, it is not necessary that we always obtain derivatives. Finding derivatives is a difficult task. So, to simplify the matters, we try to express a given function in power series, and because of uniqueness, whatever power series we obtain, that will nothing but the Taylor series for z is equal to a, and Maclaurin series when z is equal to 0 is the center. So, for this let us consider q as z square. So, we can write down this function as 1 over 1 minus q, and we know this can be expressed as 1 plus q square plus q cube and so on. So, substituting z q is equal to z square, we have power series for 1 over 1 minus z square, and it comes out to be 1 plus z square plus z 4 plus z 6 and so on. So, we do not have to calculate derivatives from this geometric progression. We can find out the power series. For some functions we can use this technique. In another example, we calculate various coefficients, or we arrive at a Taylor series by using integration. So, let us consider f z is equal to log 1 plus z over 1 minus z. Then when we differentiate this, then this comes out to be f dash z comes out to be 2 over 1 minus z square. So, we know that 1 over 1 minus z square can be expanded in this form. So, we write down 2 over 1 minus z square as 2 into 1 plus z square plus z raised to power 4 plus z raised to power 6 and so on. This is my f dash z. So, from this Taylor series I can obtain f z by integrating this series, and then I apply term by term integration of the series. So, integration gives me f of z, which is nothing but log of 1 plus z over 1 minus z. So, on left hand side we will have log 1 plus z over 1 minus z, and when we integrate right hand side it is 2 times z plus z cube by 3 plus z 5 by 5 and so on. So, this is log of 1 plus z over 1 minus z. Now, we have obtained power series representation for this function as this, but in my earlier example I have obtained the Taylor series for this function using the usual formulae given by Taylor series theorem, and one can notice that both are equivalent. In this example, we are trying to obtain power series of the function 1 upon 5 minus 3 z about z is equal to 1. So far we are considering power series of functions about z is equal to 0. Now, in this case one can notice that this function is not analytic when 5 minus 3 z equal to 0, or we say that z is equal to 5 by 3 is a singular point for this function, but at z is equal to 1 this function is analytic. So, we can expand this function about z is equal to 1 or in powers of z minus 1. So, to expand this I write the function 1 upon 5 minus 3 z as 1 upon 5 minus 3 z minus 1. So, I have added and subtracted 3 here, and this from here we can write down the series as 1 upon 2 minus 3 z minus 1, or if I take 2 outside then it is 1 minus 3 by 2 into z minus 1. So, Taylor series about z is equal to 1 is, you can expand this as a geometric progression, and this comes out to be 1 by 2 of 1 plus 3 by 2 into z minus 1 plus 9 by 4 into z minus 1 square plus 3 by 2 whole cube into z minus 1 whole cube plus and so on. Now, this series will be convergent provided this term is less than 1. So, the circle of convergence for this series is given as 3 by 2 into z minus 1 is less than 1, or we can say modulus of z minus 1 is less than 2 by 3. So, the radius of convergence is 2 by 3, but the center is at 1. Now, this is in this example we will be using partial fractions to obtain power series of given function. So, to illustrate this I consider f z as z plus 2 over 1 minus z square, and it is to be expanded about z is equal to 2. So, singular points of this function are z is equal to plus minus 1. So, about z is equal to 2 we can expand this function because it is analytic at z is equal to 2. So, to write down this function z plus 2 1 minus z square, I expand it as z plus 2 over 1 minus z into 1 plus z, and then I write down the partial fractions. So, partial fractions of this will be 3 by 2 into 1 over 1 minus z plus 1 by 2 over 1 by 2 into 1 over 1 plus z. So, now we can write down power series for 1 over 1 minus z, and I write down power series for 1 over 1 plus z here, and that will, and simplifying this, that will give me power series for z plus 2 over 1 minus z square in powers of z, but this is required for z powers of z minus 2. So, we have to rewrite this. So, 3 by 2 into 1 upon 1 plus z minus 2. So, I write this expression as 1 plus z minus 2, this is equivalent to 1 minus z, and this 1 plus z is written as 1 plus z minus 2 by 3. So, this will simplify, and expanding this we will have minus 4 by 3 plus 13 by 9 z minus 2 minus 14 by 27 z minus 2 square, and so on. So, this series will be obtained when you expand this in powers of z minus 2 and expand this in powers of z minus 2 raised to z minus 2 divided by 3, and simplify, we will get this series. There is another method for obtaining Taylor series, that is using differential equations. To illustrate this, we consider Maclaurin series for the function tangent z. For this, f z is taken as sec square z, and sec square z is nothing but 1 plus f z square, because f z is tangent z. So, we can say that f dash z is equal to f dash 0 is equal to 1. So, if f z is tangent z, then f dash z is sec square z, and f z being 0 at z is equal to 0. So, f dash 0 is 1. Now, differentiating this again, we have f double dash z, and now we differentiate from here, it is 2 times f z into f dash z, and since f dash 0 is 1 and f 0 is 0, so f double dash z is 0. Further differentiating it again, I am starting from here, I am differentiating this, f triple dash z is equal to 2 f dash z square plus 2 f z f double dash f z, and from here we can find out, we can write down that f triple prime 0 is equal to 2. This is 0, so this comes out to be 2, f double prime 0 is 0, so this is 0, and we will have 2. From here we can find out the fourth derivative, and fourth derivative is computed like this, and putting z f 4 0 is equal to this gives me f 4 0 as 0, and substituting these values we will have tangent z is equal to z plus z cube by 3, and so on. After taking number of examples, let me summarize what we have done today. We have started with some basic concepts of sequence, series and convergence. Then we have discussed that series can be added, series can be differentiated and integrated term wise, they can be multiplied term wise. Of course, I have not given you the proof for these things. Then we have developed a analytic function in a power series. We have discussed the convergence of the power series and uniqueness of this Taylor series, and then we have taken various examples to illustrate how to find Taylor series for a given function f of z. We have number of methods for obtaining this Taylor series. One is by applying the Taylor's theorem, where we calculate various coefficients by calculating derivatives, or we can use some alternative methods. I have discussed number of them to arrive at a Taylor series. This is due to the fact that Taylor series representation or power series representation is unique. So, if in any case, if in any way we can represent a function in a power series, that will be the Taylor series for the function. That is all for today's lecture. Thank you.